And we are back. Welcome back. Today we're going to talk about control variates for variance reduction in simulation. Variance reduction is a very interesting topic. Right off the bat, you may say, hey, if we have something we're trying to estimate using simulation, then clearly if we're trying to discern some sort of confidence interval for how confident we are in our estimation, you know that the standard error is somewhat proportional to the number of simulations that we run, so why don't we just jack up the simulation number? We go from 1,000, 10,000, 100,000, why not a million simulations, decrease the variance that way. Well, that's not always practical due to the cost computationally of that which we are trying to simulate. In fact, it may take way too long to reduce the variance that way, but there are other ways, for example, control variates, to reduce the variance in whatever you are trying to estimate. Now, control variates are not the only way to reduce variance in some sort of estimation of a parameter. However, it is a good way to get started with variance reduction. We're going to go over a toy example using an arithmetic Brownian motion. I'm going to connect it to some current literature in quantitative finance, and we'll talk a little bit about the implications of that. May not be directly through control variates, but I think it is a reasonable introduction to the topic, and I think it's moderately interesting to connect it to a current stream of literature that aims to improve pricing efficiency. So let's go ahead and get started with this idea of control variates. What the heck is a control variate? Well, at a high level, what's going on here is we have some sort of simulation. So let's say we're trying to figure out an option price. Classically, we pick some sort of model to model the underlying dynamics of our stock price process. Maybe we choose an arithmetic Brownian motion, geometric, maybe we do some sort of jump diffusion model. You have your pick, some sort of stochastic volatility model, whatever it may be. Well, we simulate those price paths forward, compute a payoff, and then discount them back to the present, average off that payoff, and we get our risk neutral price, if you will. Okay. In generating those price paths, we have a lot of other information available to us. We have the average price, we have the min price, the max price, so on and so forth. And that can be used as auxiliary information to aid in informing the final price of the option. Now, this will be a little more clear in a moment when we get to the actual applied example option pricing under arithmetic Brownian motion. But at a high level, what we're doing is we're using other variables, other information that we have anyway within a simulation to aid in that final estimation. And it turns out when you use other information that happens to be highly correlated with the quantity of interest, you can achieve significant variance reduction. And what that does is it leads to more precise, keyword precise, estimation. So let's take a look at this equation for a control variate here. This is actually a linear regression. And what we have here is we have this control variate, and it's important to know the control variate is not the quantity itself, but the expectation matches the quantity of interest. So let's take a look at what's going on here. Why is the quantity of interest? So you can say that that may be a European option price, for example, what have you. And then X is some sort of auxiliary variable that you're going to have that's highly correlated with the target quantity of interest. All right. Now, what you'll notice happens here is we have the expectation of X. So if we have some sort of model whose dynamics enable us to have in closed form the expectation of, say, the stock's price at the maturity, then this is going to be extremely correlated with the target quantity of interest, and we're going to achieve variance reduction. If that's a little too complicated, then let's just take a look at what happens when we take the expectation of this top equation here. That's what's going on down here. So remember, y is the target quantity of interest. I'm going to take the expectation of both sides. So when I take the expectation of both sides, I'm going to substitute c in for this y, And you can see that the expectation of the control variate is going to be equal to the expectation of the target quantity of interest. And why is that? Well, when you take the expectation of the right-hand side, what happens is, due to the linearity of expectation, you can distribute the expectation through. C is just a constant. We select that value. And you distribute the expectation through. It gets assigned to this x. It gets assigned to this expectation of x. Clearly, the expectation of x is just a constant as well. And they end up canceling each other out. This is what allows us to use the information from that auxiliary variable to inform the estimation of the target quantity of interest. Because the control variate itself, that value, is not the quantity of interest, but the expectation of that control variate is the same as the expectation of the target quantity of interest. In other words, C sub CV is not C, but the expectation of C sub CV is the expectation of C. Okay? How is C chosen? Well, we minimize the variance of the estimator through very simple optimization. You can go ahead and take the derivative, set it equal to 0 if you like. Turns out C is going to be covariance of yx divided by the variance of x, and of course this is just a linear regression here. But if we had the covariance of y and x and the variance of x, we would not need to do this, because we would have the target quantities expectation. So we're going to need to use the sample covariance and the sample variance to estimate this constant C. And that's what we do after simulation. How does this reduce the variance? Well, if we take the variance of both sides here, we can see that the variance of the control variate is going to be equal to the variance of y less c squared times the variance of x. But you'll notice here that if you substitute this quantity in here, that the more that the covariance, this is going to be, I believe this is going to be just the more that the two quantities are related, turns out that the more variance reduction you will achieve. So in other words, the more valuable the information is of x within each run of your simulation, the fewer simulations you have to run to achieve similar precision. And that's exactly what we have here. If you take the variance of both sides, you can see that you end up actually with a correlation term here. And this correlation term says that, maximum variance reduction is achieved when correlation is 1. Clearly, correlation can't be 1 because you would have the target quantity of interest expectation anyway, but if they are highly correlated, you're going to achieve significant variance reduction. So that is the gist of control variates for variance reduction. We have this linear regression here. You're not limited to just one auxiliary variable. You could do a multi-regression as well. So you could, add a z as well if you like. You could do, more than one auxiliary variable to decrease the variance as well. But this is just a very simple, hopefully simple example here in the context of pricing. And this is the general gist here, is you can see that since variance is going to be positive, variance is going to be the expected deviation away from the mean, you will go ahead and see that if you subtract some sort of constant times the variance, you're going to have less variance than the variance of the original target quantity of interest anyway. Okay, so how does this relate to a practical example? That was a lot of theory for those of you interested in the theory. Now we can go ahead and talk about a practical application in pricing options. So here we're choosing an arithmetic Brownian motion. This is unnecessary, right? Like we have a closed form solution Bachelet. We don't need to use control variates here. But this is a very intuitive example, and I think it's more fun than just seeing it applied to something random like some sort of queue, a continuous time Markov chain or something like that. So let's just take a look at it in the context of option pricing under ABM. So we know that the call option at maturity has a payoff function of S of t minus k and 0, whichever one is larger. Our hockey stick diagrams, if you will. And we know that the dynamics for the underlying asset are given under arithmetic Brownian motion by this equation here, where we have an initial asset price, we add some sort of drift scaled by time, and we add some sort of volatility scaled by sigma. And the volatility is just a standard Brownian motion. What we can do is we can add a control variate to aid in the estimation of this European call simulation. So we're trying to simulate the price of a European option. We are going to simulate a whole bunch of ABM price paths to maturity, calculate the payoff, discount it to the present. We're going to get the average of that set of values, and that'll be the approximate price of the call. Now, there's going to be variance, and what we want to do is reduce that variance so we don't have to simulate as many price paths. What we can do is we can use the arithmetic average of these simulated prices, because we know under arithmetic Brownian motion that the expected price at maturity is going to be the initial price plus mu times the maturity divided by 2. That is going to be our control variate. Notice how the dynamics of the model that we've chosen, arithmetic Brownian motion, enable us to have this known value for the expectation at time cap t. Okay, that's very important. Now, is this kind of redundant? If we know this, do we really need to simulate price paths? Probably not. But bear with me, it's a toy example here, because clearly if we have the expectation at time cap t, then this is completely redundant, right? But let's just take a look at what happens here. So what we're going to do is we're going to run this simulation. So I'm going to have the initial price, our strike price, time to maturity, a drift, a volatility, certain number of simulations, and time steps. So initial stock price of 100, a strike of 100, time to maturity of 252. We have 252 days. We're going to do daily time steps, 252 steps. We have a 10% drift, a 30% volatility, and we're going to do this 10,000 times. I'm going to go ahead and run this guy here, and we get this interesting output. So let's go ahead and take a look at what's going on here. So we have our original payoff distribution. That's this blue distribution here. And this is the average payoff of the simulated prices. Or these are the payoffs, I should say, of the simulated prices. You'll notice that the adjusted payoffs with the control variate has a tighter distribution. Now, that doesn't necessarily specify the payoffs. Remember, the control variate is not the payoff. If we go back up to this equation here, we can see that CCV, that value CCV, is the target quantity of interest less the information added by our auxiliary variable. So CV is not the value of the payoff itself. It is our control variate. And we know that if we take the expectation of our control variate, then we get the expectation, the estimated target quantity. That's what we're looking for. So when we come down here, that orange density is not the same. It's not the same as the blue density in the sense that that is our control variate distribution. Okay? The original payoffs is the blue distribution, but you'll notice that the expectation is the same, but variance reduction is achieved. So how can we see this? Well, the original call price is going to be 25.14. The adjusted call price estimate with the control variate is 25.18, but you're going to get different values every single time you run it and as you increment more simulations. So what's a good measure for the variance reduction that is achieved? Well, one way to look at that is to take a look at the confidence interval under the same alpha value. And in that sense, you just take a look at the standard error, and you can see the original standard error is 0.05, and the adjusted standard error after introducing the control variate is 0.02, which gives us approximately 75% variance reduction. So under the same alpha value, in other words, we are 99% confident that the price or the interval contains the true price, that interval is tighter and it costs us the same amount of computational power. Now, that's a little... that kind of ties this whole thing together here, I should say, is fixing all of those things, we have a tighter confidence interval. So using the same amount of compute, using the same amount of price paths, in addition to this control variant estimator here, we are going to get a tighter confidence interval, and we didn't have to increase the number of simulations. All we're doing is we're using the fact that there's this auxiliary variable that can contribute information to the target quantity of interest. And that is exactly what's going on here. So this is with an arithmetic Brownian motion, but how do we connect this to what's going on in the current body of literature, recent literature, I should say? Rough volatility model is a good example of when this might be useful. May not be explicitly in the same context here, because if there was a closed form solution, then again we wouldn't need to do this. The actual auxiliary variable you may use, or the technique for variance reduction, is probably different, but I wanted to connect it to something that is practical as well. So a rough volatility model, for example, it introduces a long-range dependency. It's non-Markovian in structure. It is going to depend on the entire price path. So it's very expensive to simulate a single path of a rough volatility model. So the idea here is, if you wanted to use a rough model to approximate some sort of option price, whether it be some sort of vanilla or exotic product, you're going to need some sort of variance reduction technique, because simulation is computationally expensive. It's very expensive. And if you wanted to, think about how many options are on books every single day that need pricing. Efficiency is a big deal in this line of work. So something that has a closed form solution, even though it may be less accurate, if you will, definitely has more value in that context. So a rough volatility model may better characterize the dynamics of the markets, but if you can't do it efficiently, if you're pricing things that needed repricing last week today, then it's not helpful. But if you have some way to maybe increase the efficiency of your estimations by doing variance reduction, then it could be particularly helpful. Connection to the current literature is approximation of these models, these pricing functionals, using neural networks. So, one way to do that is to essentially map, you're going to create a parameter set map of the model's inputs fit to a surface, and then you're going to have some sort of surface as an output, and you're going to try to learn that relationship as essentially just a map. And then, since a neural network is just a function, you can actually use that to, efficiently price your options. And then you're actually using some sort of optimization routine to try to maybe even fit that to a volatility surface to reprice, so on and so forth. So I have other videos discussing that in more depth if you're interested, but that is just the general gist of what's going on here. Is the overarching theme is it is computationally expensive to simulate these models. So what can we do? Well, there are current streams of literature that aim to try to approximate these maps, approximate these pricing functionals using volatility surfaces and the model parameter set. And the whole goal there is efficiency. But efficiency is in the same context. If we simulate a whole bunch of paths, then we need to simulate a lot of paths because we need good estimation of parameters. And in this sense, we need a good estimation of the option price. What is good? Well, why do we simulate a lot of paths? We simulate a lot of paths to hope to reduce the variance and find what that true price actually is under a specific model framework. And that is why you would need variance reduction, specifically due to efficiency. So efficiency is a very big problem. There's kind of this inverse relationship where as complexity increases, efficiency decreases, and vice versa. Simplicity can be, it can be very useful. It can be very useful, especially if you have a closed form solution. So that's kind of like the gist at a high level of variance reduction. Hopefully that's an interesting link to the current streams of literature in finance. And I think that's going to do it for this video on controlled variance and variance reduction. I hope you enjoyed. If you have any questions or comments, please feel free to leave them in the comment section below. Join Discord if you have anything you'd like me to address directly. I tend to be more responsive there, but I hope you found this interesting. I hope this was a fun toy example to illustrate variance reduction. Clearly it's a toy example because if you have the average stock price at maturity under a specific model, then why on earth would you need the simulation in the first place? Nevertheless, toy example. Hope you enjoyed it, and I will catch you in the next video. Thanks for watching.